All right, hopefully you're starting to ease your way into some final review information. There's a lot of it. Um, so try to spread it out and don't save it all up for the end because you'll probably run out of time. As you do begin to study for all of your finals, please keep in mind general life lessons and rules. Make sure you try to have fun. Please try not to hurt people. Do not accept defeat. And even though you may be stuck in your house, strive to be happy. This is just a couple key pages from previous years that have helped people. This is from Unit 1, which is a massive unit. I mean, almost 100 pages worth of course pack. Probably the last 15 of those were answers, but still, 80 something pages, a lot of information. Your first 3 pages, right, 1 through 3, was all vocabulary. It's totally worth going back and just reading through those words one time. Um, you know, have a list, a note card, something, so that if you do come across something that you don't remember at all, or that you maybe never truly understood, maybe jot that down and you can ask about that later. But 3 full pages of vocabulary took us like 2.5 days to get through all of that, and then we use those terms to analyze a lot of our math, throughout a big chunk of the rest of the semester. Um, from pages 9 through 13, we started cataloging our parent functions, and when we went into each parent function for a day, or in some cases two, at a deeper level, we would go back and fill in a lot of the information characteristic to that function, domains, ranges, whether or not the function might have increasing or decreasing intervals, its boundedness, things like that. So those like 4 pages or so would be worth checking out. On page 67, as soon as we finished transformations, there was a 1 page that had all the parent function graphs on it. So it didn't have all the detail, but it definitely had all the pictures of the parent functions. And that's a nice little reference page if you've forgotten what the parent functions look like. If you can understand why the parent functions have the shapes they do, it'll go a long way to helping you not have to memorize them. You'll just kind of understand why their shapes are what they are. Page 124 was a huge page because it was our notes on rational functions, which we then used for 2 assignments during January, but then we came back and did in I think late February a much deeper look at rational functions and some of the strange things that can go on with them, like jump gaps and holes being covered and horizontal asymptotes being crossed. There's actually a very detailed page of notes on the rational functions, even more so than what you have on page 24 on our calendar. So if you go back into late January 20 something, I can't remember the exact date, but when we covered rational functions, there's a PDF file from our lecture notes that I went into great detail to add a bunch of information to, worked out examples, and it's all just sitting there waiting for you. Um, Go back and take a look at that. Some of these pages I haven't read aren't big, over-encompassing ideas like terminology or parent functions, but they're types of functions that students have told me they struggled with on the past. Coming out of the final, they'd say, I really wish I would have studied these more, or I didn't remember these very well. Um, from about page 29 through 36 or something like that, maybe even up through 40, there's a whole bunch of information on logarithmic and exponential functions. I mean, first we went back and we reviewed rules and properties of logarithms and exponents, and then we analyzed the functions. And I think analyzing the functions wasn't as much of an issue for folks. Um, you do have to be careful with the domain of the logarithmic functions, understanding that the argument must be greater than 0, not greater or equal to 0, strictly greater than. But a lot of the log properties, trying to manipulate and change the logarithmic proper equations, so they can be solved, or convert them into exponential equations and those kinds of things, change a base formula. People have told me in the past that even though there aren't a ton of those types of problems, that those are some of the problems they've struggled with. The trig graphs, you saw so many basic trig graphs in the fall, but it's been a while. And so some people have talked about how we just kind of review the trig graphs and then they don't go back and study them for the final. Plus we did some new things. I mean, for some of you, the phase shift and vertical shifts were a little bit new, but more so the inverse functions. The inverse trig graphs are things you hadn't seen before, and so you might want to review that. I think specifically on page 56 has a nice page with all the inverse trig graphs and domains and ranges all kind of together. And then finally, page 59 was the greatest integer function, which was probably the newest of all the functions we looked at this term. Uh, regarding parent functions, with its kind of stair-step nature and its infinite number of jump discontinuities. It was very different. And so page 59 is a page of notes on what the definition of that is. Sometimes people just forget what it means, so you'll have to evaluate like negative 5.2 greatest integer, and they'll say, oh, that's negative 5, but the definition is the greatest integer less than or equal to, not greater than or equal to. So negative 5 is actually greater than negative 5.2. You'd actually have to drop down to negative 6. And people get themselves in trouble with that function quite a bit. And then finally, a massive thing that we worked on, quite honestly, all through the parent functions and through this stuff, was the transformations. And then finally, once we were done with the parent functions, we came back and spent a huge amount of time, I think 2.5 days, just working with transformations, um, understanding what each of these operators A, B, C, and D do to a function. And pages 64 through 66 have detailed notes explaining kind of why the functions change the way they do. But on page 66 specifically, there's a chart that combines all of the information, so you can very quickly reference what does A do, what does B do, what does C do, what does D do. And you'll see as we start going over some problems why that might be a really good idea for you to do. I did have about a half dozen questions that were posed to me throughout the day yesterday. Problems 1 and 2 right off the bat were two of them. Identify the intervals on which the function f of x equals x squared over x squared minus 36 is increasing, and then identify the intervals on which the function x cubed over 9 minus x squared plus 1 is decreasing. So this one I think is a little more easy to predict. It's a polynomial, and it's a cubic, right? So it's going to behave like a cubic. It's a positive x cubed. So there's really only two shapes that graph can have. It could come up and then kind of move over a little bit and then keep going up. So it never really changes direction, but it just slows down and then speeds back up. You'll learn in calculus this point is called a point of inflection, where the concavity changes, although the direction doesn't necessarily change. Cubics could also come up and then bend back down and then go back up, right? And that's another possible shape for the cubic. We might as well do number 2 since we are up here, and I have a picture of this particular graph. I graphed it, and sure enough, it looks like one of those two shapes we just talked about. Now this asked, specifically, when is it decreasing, right? When is it decreasing? And so as we move across, it's definitely increasing up to this local maximum, and then it decreases to this local minimum, and then it increases the rest of the way towards infinity. And so the only decreasing interval is from, it looks like, this this x value here to this x value here. And I went ahead and found the values using the calculator. I did the analyze max, analyze min, and found that the maximum, the local max, occurred at x equals 0, and the local min occurred at x equals 6. And so now I know the decreasing interval for this function is from 0 to 6. And that's pretty much all they wanted to know. If we go back and we look at the options now, this is this looks like where it's increasing, outside of that interval. Here's the interval we're looking at right here. Now, this is a little interesting that it gives you both 0 to 6 and 0 to 6. I would actually accept either one of those, to be quite honest. I think even the AP test would, because there's arguments among mathematicians whether functions are actually increasing or decreasing at those local mins or maxes. I think you could argue it both ways. And so I think most of the AP literature, like on the rubrics that they offer students, use the closed interval, but they accept on their test, they accept either way. So I'm a little surprised that I haven't gone back and taken this one out in the past. That one really shouldn't need to be there um, for that. Um, moving along, let's hear problem one. I have a little outline down here I want you to examine, and I just want you to talk through this. Like, what if you weren't doing this with a calculator? So, I mean, I know that the denominator is difference of squares, right? It's going to be x minus 6, x plus 6. So there's two zeros in the denominator that are going to make this function undefined. One at negative 6, one at positive 6. And as I look at the top, I realize neither one of those is going to cancel with the x squared on top. So that means they're both vertical asymptotes. So I have two vertical asymptotes, one at negative 6, one at positive 6. And, just as an added bonus, I look at the end behavior. X squared over x squared would be the end behavior model. And I know that's 1. So I know that at 1, there will be a horizontal asymptote. So I can very quickly get this framework of how this is going to work, or kind of look, in the long run. And I also know that because of that horizontal asymptote and the converging end behavior that it's going to have, that it's going to be approaching this horizontal asymptote either from below or above forever. Um, the big question, I think, is what direction is it coming down from the asymptote? Is it coming up? Because if we want to know where this function is increasing, we're going to need to be able to analyze that. That's going to be the big thing here. And so that's why I have all these little numbers here. Because if you did not have a calculator, you would have to do some little tests. You'd have to say, a number that's just a little bit to the left of negative 6 would be like negative 6.1. A number that's just a little to the right would be like negative 5.9. And so you could plug these in to the function, and you're not looking for a value as much as you're just looking to know whether it's positive or negative. So if I plug a number just a little to the left of negative 6 in, the top is going to be positive every time because I'm squaring it, right? It's always going to be positive. Now the bottom, this value will be squared, but then I subtract 36. So any number that's bigger than 6 or less than negative 6, once it gets squared, is going to be bigger than 36. And so then my difference down here would be positive, meaning that if I put a negative 6.1 in here, I'd get a positive on top, a positive on the bottom, I'd get a positive. In fact, I'd get like 36 point something on top, and on the bottom I would get 0.1, well, 36 point whatever minus 36 would be a very small decimal. It would be a larger positive number. See, this tells me that this guy is going up on this side. So it's probably going to come down and then approach the asymptote from the top, kind of like that. Okay. Now on the same method, using the same method, I could take negative 5.9 on the other side, very close to negative 6. I could plug it in the top and say, oh, that's going to be positive because I'm squaring it, right? But on the bottom, when I square it, even though the value will be positive because it's less than 6, the square will be less than 36. It'll be a little less than 36. So when I do this number squared minus 36, I'll get a negative. I'll get a positive on top and negative on the bottom Well, that's going to be a negative number, isn't it? So that would actually be going down this vertical asymptote. Okay, I actually know that 0 is going to be a 0 because if I plug a 0 in, the bottom is negative 36, but the top is 0, so that's just a 0. So 0, 0 is a 0. And then if we test it on the other side, what you'd find is that it has similar behavior on the other side, kind of like this. So this is what this function would look like, okay, if you graphed it all out. Now remember, the problem asked us, where is it increasing, right? Where is it increasing? So now that we have our sketch, we always start from the left and we move across. Oh, it's increasing from negative infinity until I get to negative 6. And then on the other side of negative 6, it's increasing until I get up to this local maximum at 0, 0. And then the rest of the graph is decreasing, isn't it? It's decreasing in this interval down toward negative infinity. And then as I come down from positive infinity and infinitely get closer and closer to a value of 1, it's decreasing there too. So it's decreasing in these two sections, but increasing in those two. So you could do this, you could analyze this graph without, without graphing it, without too much computation, just a little bit of thought. And that's what this whole class was really supposed to be about, right? Math analysis. If we go up here and look at the answers then, and we say, all right, so from negative infinity up to negative 6, well, we see a problem right away here, and that this one goes up to positive 6, and it would be including the asymptote, so that's no good. You can't include the asymptote. This one starts at 0 and goes to 6, so we don't want to include that. Now this one goes from negative infinity up to negative 6. It doesn't include negative 6, so that's good. And then it starts at negative 6 and goes up, and it does include the endpoint 0. And so I would also say that that one is good. Now, once again, I don't I don't really like question D because it's really the same. Well, no, I guess they left a negative off here, so it really doesn't make sense. But otherwise, the only difference is whether or not we're including 0 or not. Like I say, even AP doesn't distinguish on the end of an interval. That's the end of an increasing or decreasing interval, whether that's included. So, but in this case, C is the only one that has the right numbers the rest of the way through. You're not going to be limited like you would in class where you have 30 non-calculator questions and 10 calculator questions. So that part of the final should be a little bit easier because I guess the whole thing technically is a calculator, test for you. I don't think normally you'd have time to graph every single little thing, even if it was, but since you'll have a fairly large window, what we've been giving you like 6 hour or so windows to take these tests, you could probably graph it, and you get a graph exactly with what we just did. And so it's very easy to see where those increasing and decreasing intervals do exist. Okay. So that's problem 1. Problem 2. The next problem wasn't until problem 9, so let's move towards that direction. Notice how many transformation problems you'll find along the way. This one's talking about vertical stretch and horizontal stretch and then a vertical shrink. And so that's really understanding your A and B values pretty well. A values are pretty easy. You just multiply the you know the whole function by the stretch value, and so you can see distribution would give you answer D on this one. The horizontal ones are a little trickier because you got to make sure that you bury that number inside of the function, and then if they did take everything to the fourth here, this would actually be 1 over 16 x to the fourth, and that would be the same thing as C. And so you do have to be a little bit careful about how those are written with the horizontal stretch, the B values, right? Number 6 was another, horizontal shrink, so we had to make sure that 1/5 got put inside. By the way, this was a shrink, and so it actually should have been in this one an answer of D. Because we'll get to this in a second. These are some of the questions you guys are asking about that B value. Number 7 and 8 are transformation questions. Number 7 gives you the rational function and wants to know how it's moving around. We always know that just 1 over x would always start with a horizontal asymptote at the x-axis and a vertical asymptote at the y-axis, but this one definitely has been shifted back. It looks like 3 units, and so I need to shift 3 units over, and immediately that's going to get rid of, this one's 2 units to the left, this one is 3 units to the right, this one's 3 units to the right, so those are all bad. Also, we see that our vertical or horizontal asymptote, I should say, is shifted up 2 units, and so we need the +2. Well, both of these have +2, so the only difference really is that this one has that negative, and that's actually going to be why we choose D to be the answer, because normally we get kind of our graph in quadrant 1 and our graph in quadrant 3. Well, you can see that these have been reflected. It looks like this one got reflected down here and this one got reflected up here, hence the negative on the outside of the function that reflects us, you know, vertically through the x-axis, or I guess in this case the horizontal asymptote. All right, number 8. It was an exponential function, and normally exponential functions have two very key things going on. They have a horizontal asymptote at 0, and they have a point on the y-intercept at 1, because anything raised to the 0 is 1. So you can see this one has that value. The problem is it's been shifted. It's been shifted 2 units to the right, based on what we see with the C value there, and it's also been shifted 1 unit down. And so not just the horizontal asymptote would get shifted 1 unit down, which we can see would be a problem anyway, because well, I guess see, it still looks like it crosses it, but this point would have shifted down too, and it didn't. And so that can't be the answer. Same thing here. This one with the shift down 1 unit, it's already crossing that, so that doesn't look viable. This one looks like it has a vertical asymptote at 2. This one looks like a logarithmic function. This one, if we shift down 1 unit, it looks like we're crossing at where the asymptote would be. Well, maybe just a little bit above, but I think if you shift down 1 and then over 2, you actually run into the point that you're looking for there. So that one actually looks good, as far as what we're trying to match up. This one, once again, crosses the horizontal asymptote at -1. That one wouldn't work just because of that reason alone. So I think C is the one that has the horizontal asymptote in the right location at -1, and then it moved that intersection point that we knew, down 1 unit over 2 units. That's the one I think we were looking for. All right, number 9 was actually requested. So let's take a look at that one. It was asking the solutions for this kind of ugly looking function. My guess is most people would probably miss this one because of this part right here. And it's not the natural log part of it. It's the brackets. Those brackets are a very specific function. Those brackets are the greatest integer function. And so you need to make sure you put in, I think, either int into your calculator. That would accept it, int, or I think you could type in floor, floor, floor would also work for the greatest integer function. You could either do both of these set equal to each other, 2 different functions, or you could set it equal to 0. I think the way I did this one is I set it equal to 0, so you can kind of see how I typed it in. And you can see that I put the natural log, and then I used int for that, for those brackets, and then the rest of the function. And then I added that cubic from the other side over so that the whole thing was set equal to 0. And I just got this one big function here. And because I set it equal to 0, I'm really looking for the roots. Of course, when we look into this area right here, it's kind of hard to tell where the roots are. And so what I did is I zoomed in. I think I just did a little zoom box. That's probably the easiest way to zoom on a function like that. And this is the graph I got. You can see that the graph is broken into a bunch of little different pieces. That's due to that greatest integer function's influence on the graph. But this is what you would see. So there's two zeros, and once I was zoomed in, it was very easy to have the calculator find those zeros for me. I just hit, math or menu analyze, and then zero, right? Either zero or root on the calculator. But that's how you tell it to find those two spots. So negative 2.930, negative 1.907, and that matches up with answer B for that one. So if you asked that problem right there, hopefully that helped you understand that. Number 10, yeah, same type of thing. Graph it on your calculator and then use the analyze, maximum values and find the maximum values on that one. I think it turned out there were two of them. I think F was the answer on this one, A and D. Number 11 and 12, we were actually number 11, I guess, was where we were plugging the function in and then just having it evaluate our value of 35. 12 was actually an end behavior function. And this one you have to be a little careful because I think there may have been a lot of people who saw the 2x to the fourth, so they're thinking positive even, which would be like a parabola, right? So that would be like an up. And so if you said A on number 12, my guess is you just didn't look and make sure you found the degree, which ended up being negative lead coefficient and an odd. So it's going to behave like a negative x or negative x cubed. It's going to have down up and behavior like this guy. So that's why the answer on that one is D. And that was number 12, 13. Okay, so 14 and 15 are the ones that get asked every year, and guess what? They got asked again this year. And so this is where that transformation stuff really comes in. So let me talk to you about that. Here's the thing. I think that people look at this this function here, and they just think, well, I know that the 4 is inside, so I'll multiply the x by 4, and the 2 and the negative 5 are outside, so I'll just multiply by 2 and subtract 5 from the y, and then that'll work. But see, this isn't. You don't know what f is. You have no idea what f is. So you don't really know what's going to happen with the 4 and the x. The y stuff is more predictable. You could pretty much just multiply your y value by 2 because that would be stretching the y value, and then subtract 5 from it because that would be, shifting it down 5 units. But that's not how the interior works. And what I always tell people when they ask me about this problem is go back to your transformation notes. Until you understand your transformation notes, you're going to keep missing these every single time, because these problems were in the transformation assignments, and then they were on the transformation quiz, a little quiz we had back in like February, and then they were on the unit review for unit 1, the second big test, and then they were on that test. I mean, you've seen these like 4 or 5 times, and people still don't do them right. So that means you either do not understand, or you haven't really studied it enough to memorize it. Once you understand something, you won't continue to make the same mistake repeatedly. So, page 66 is what the page I highlighted that has all these on them. And I went ahead and printed it off. This is the chart I'm talking about right here. Okay. And this is where people just don't get it. If B is greater than 1, and if it's negative, then it would be less than -1. Its absolute value is greater than 1. It is not going to get bigger like the A value would make the Y values bigger. It's actually going to get smaller. It's going to be horizontally compressed, not horizontally expanded. On the other hand, if the absolute value B is smaller than 1, then it will get horizontally expanded. You can't just go in and multiply and divide. You don't even know what that function f is. You have to follow these rules. And so if you never learn those rules, that's a problem. So I would go back to Unit 1, page 66, maybe even read through 64 and 65 to get a little background information so that you truly understand this equation. Okay. Now, with that being said, most people will get the y value right because they'll take they'll take this -2 and they'll double it, right? So they get -4, and then they'll subtract 5 from that to vertically translate it down 5, and they'll end up with a -9. And so I think most people are going to say the answer is B, because they're going to take the x value here, and they're going to say, oh, I'm just going to multiply that by 4, because it says to say 4 times x. But this isn't the function. The function isn't multiplying by 4. Multiplying by 4 is inside of a function that we don't understand. We don't know what it is. So we have to follow the rules of transformations, which say, once again, I'll point this out one last time, if b is bigger than 1, it is a compression. It's a compression. That means it's getting smaller by a factor of 4, not bigger. Okay, and so we need to take this value and not multiply it by 4. We need to divide it by 4. Now, if this was a 1/4 in here instead of a 4, then I would multiply it by 4, but it's not. And 4 divided by 4 is 1. And so that's why the answer for number 14 is A. Similarly, on number 15, we take the y value. The y value is usually pretty easy to work with. It's going to be vertically stretched by a factor of 3 and then reflected through the y-axis. But if you do 3 times 6, which is 18, and then reflect it through the x-axis, you get -18. That's the same as just multiplying -3 by 6, -18. Oh, and then let's add 7. That takes us back to -11. So we know that the answer's either got to be A or D, based on that. But I think what a lot of people do is they just plug the x value in and say, oh, I'm just going to add 5 to it. And, -2 plus 5 is 3. And so they say the answer is A. But that's not what your transformations say, once again. Okay, let's read those transformations for the C value. If C is greater than 0, we go to the right. But remember, the natural state of the function is -c. So the fact that you're seeing a +5 there really means that C had to be a negative value, -5. Okay, and a -5, so that's this part right here. If C is less than 0, we're going to translate to the left. Now this says C over B, and if there was a B value, you would have to do that. Our B value is just 1, so we're just going to move to the left C units. And if we're starting at -2 and moving to the left, we would end up at -7. And that's why the answer for this one is D. Okay. All right. 16, factoring, 17, factoring, 18, solving inequality, which involves factoring, right? We had to set equal to 0. And then we had to translate. What is this really asking us? Well, it's asking us, where is the graph? Because this is less than, we'll call that below the x-axis. So that's how you know what part of the function that gives us our solutions. But all of these involve factoring. Factoring was a huge important skill throughout this entire semester. So I hope you understand how important knowing how to factor is. Another inequality, number 19, just a linear equation, right? We're looking for perpendicular line. So first of all, you would have to know how to find the slope of this line. And you could either use the shortcut formula, m equals -a over b, or you could just solve for y and understand that it was going to be, I think, a slope of 3. But then the perpendicular slope is the opposite reciprocal. So the opposite reciprocal of 3 is -1/3. So I think based on that one fact alone, you get your answer. The only possible perpendicular slope for this problem is -1/3. You wouldn't even have to plug the point in with that slope if you just used the slopes. What were we doing with 21 and 22? Solving. So we did one of those up in the rest of the problems. 23 and 24, we were finding extrema, so local mins, local maxes. Maybe those local mins and maxes are absolutes. That would happen with even polynomial. So this one, because it has down end behavior, would definitely have an absolute max. This one is a 5th degree, so it has down up end behavior. So it would not have an absolute min or max, right? 25 through 28 were problems you had to put in your graphing calculators and then evaluate. And I did get asked about number 25. And once again, it may be that people just thought these were brackets here, this part of the function. Those aren't brackets. Those brackets mean greatest integer function to us. And so we have to, we have to plug it in. That's the greatest integer of 1/3 x plus 5 minus 2/7 x squared, and this is the graph you would get. If you do put that in correctly, then what you do, you can just go to your trace menu. So you go trace, graph trace, but instead of tracing to like wherever they ask you to, you just immediately type in the value. So like I wanted to know what 9 was. I just plugged in a 9. A little box will come up as soon as you hit a 9. It'll say x equals, and then you're pretty much done. It'll give you your answer down, at the bottom um, what the y value was. So in this case, negative 15. Um, 0.143, and then the other one, you wouldn't even have to change screens. You're already trace mode, so you could just re-enter a new number, which is negative 17.25, and you get negative 86.018. 29 and 30 were synthetic division problems, so you had to use synthetic division and then the quadratic formula. Nobody asked about those, but if you did want to know how to do those, we had our notes on those are back in the unit 1 teens, kind of maybe around oh heck, I don't know, 17, 18, maybe one of those pages of Unit 1. You could also go to the calendar and see all the worked out solutions back in January, whatever we did roots. All those worked out examples, PDFs are all there. All the notes we did all year are still on our class calendar, so you guys can go and get anything you need. Nobody asked any matching questions. Once again, knowing your parent shapes and understanding transformations is important for doing this. So hopefully I was able to address the questions that were asked. I imagine you guys are into review 2 now, which was still covering Unit 1. That ranges from pages 4.5 through 4.8 of the review. You guys should have all the answers, right? I shot those out as a PDF yesterday, so make sure you check that out. A lot of rational function stuff, which I know are trickier problems, some piecewise functions, a little bit with some of the different types of functions we did, even roots, maybe an odd root in there, logarithms, and exponential functions. A little bit of all of those types of functions, and then definitely some exponential and logarithmic type problems at the end. I know people get freaked out because there's a lot of different ways of solving, or at least of seeing those. There really are only a couple ways of solving them, which I can understand, but there's not going to be like 12 of those on this test. There might be 1, 2 max. So ask any questions you want. Get them in to me sooner the better, and I'll do an answer video for you again. But I wouldn't freak out about them too much. Keep in mind that you know more than you think you do, right? If you've been in doing all the videos, coming to class early in the semester, you know more than you think you do. Trust yourself. You really do know it. You just got to remember it. And if you're not understanding it, ask questions. Have a good Wednesday.